Okay. So for everybody else who showed up late, once again, thank you for hanging out for the last session, because I know I've left early for things. This is normally an hour-long presentation. I'm going to be, YouTube at 1.3 or whatever it is to try to get through it quicker. Very briefly, my background, I've been doing multi-threading, I guess, since 1997, but if you count multiple processes talking to each other as a form of multi-threading, then since 1991. So the agenda really quickly is we're gonna talk about what is exactly multi-threading, advantages and disadvantages, hidden multi-threading, where you might be doing multi-threading without knowing about it, or knowing about it but doing it as what I would consider a low level. How are threads used, tools, we're going to skip for the most part, and then best practices, which is, I think, the most important part. So, let me wander over here. The main reason for using multi-threading is, here's Moore's Law, and right around here in 2002, 2003, Moore's Law stopped working for you if you were doing single-threaded code. Because we stopped, when I had my first computer, 1982, I think it was 6 or 4 hertz, and we've gone all the way up to gigahertz. Around here, we went to multiprocessors. My phone has 4 CPUs in it, right? My computer has 8. So if you have a single-threaded application on your computer, this is you, right? Here's the operating system. Maybe you call the operating system to do something on the disk, so that's that. Maybe this is other stuff going on in the operating system, but all these other CPUs are doing nothing. Which, if your application isn't all that busy, isn't a problem, but if you're trying to get a lot done, you're basically wasting resources. You're actually here. Sometimes when you drive by the construction site on the side of the road and there's one guy digging or doing something and 3 guys standing around, that's you with multi-threading, right? So in a traditional, well, actually we're going to skip through this because we're going to get to it later. So the advantages, like I said, is you can able to complete tasks faster. You can be more responsive. Think about it this way. You can have one register open at the supermarket or at Walmart or wherever, and everybody is piling in, or you can have 10. And if you have 10, not only can you get more people through, but it's more responsive because you've got the one little old lady with her coupons who's arguing over the discount, whether or not the sale applies to the item she has. She's only blocking up some people, not everybody. So it's more responsive, you can get more done, get things done faster. You can also prioritize. You can go and say, this is important work, this is less important work. You can delay the less important work until all the important work is done, or in between the slots when the important work is completed. This is sort of important when we talk about how what I'm talking about is different from, say, serverless applications. You're able to share resources within the same processor state. It's more efficient to do it that way. Once again, depending on your application, if your tasks are all completely independent and stateless and don't have to communicate, this isn't an advantage for you. My experience is most applications are not completely stateless, and so this is where you get some sort of a benefit. That's sort of like the lower priority. While you're doing work, other things can be killed. When there's no work, lower priority things can be doing things. I think that if you design for multi-threading, you're also adding in better separation, specialization of tasks within the code. I think the code itself is better if you put in the effort. But once again, maybe you don't have to. It opens up the possibility expanding to multiple machines. If you've separated out the tasks, then if you can't process everything on one machine, you're in a better position to be able to enhance performance by spreading out onto multiple machines. Disadvantages. What exactly did you say it was? It was horrible problems or something?
I just said it was scary.
Scary, scary, right? So you have to put in some time and effort to design and code. And once again, if you don't need multi-threading, then you don't need to put in this effort, but it's there. So, your scary part, I think, is what they call Heisenbugs. Basically bugs that, and actually it's even worse than Heisenbugs, are basically bugs that change their behavior or more likely disappear when you're looking at them or looking for them. So some of these things, particular race condition, is if you've got two threads and they're going through the code, sometimes this thread gets ahead of this thread, sometimes this thread gets ahead of this thread, and sometimes if it's just the right amount of ahead of the other one, you can have a bug. Which means you can have a bug that happens every 3,000, 10,000 times you go through that code. So somebody reports the bug, QA goes through and they try it 3-4 times and they say, we can't duplicate it. It doesn't exist. But then another customer calls and says, this happened to me too. And then everybody's trying to figure it out. You go through your debugger, you can't see it, you're testing it, they're testing, nobody can find it. So that's your problem, Heisenberg. Memory corruption is worse because you can have two threads accessing the same data at the same time, and that can be a problem. You don't want something in particular, you don't want to grab some data, start processing it, have another thread grab the exact same initial state of the data. This one finishes processing, writes the results, and then this one comes along and writes new results, which had it grabbed the end state of the first thread would have been different from what it generated using the first one. So there are ways of preventing that. The other deadlocks. Deadlocks happen when two threads need the same resources, but they grab them in the wrong order. So imagine that you've got a crew of people framing a house, and general contractor, I guess it's cheap or something, and you've got one nail gun and one air compressor. If one worker grabs the nail gun, and he's like, okay, I'm gonna wait until the compressor gets free, and one person grabs the compressor and says, I'm gonna wait until the nail gun is free, they're both going to be waiting until the end of their shift and do nothing. You have synchronization bottlenecks. Basically what that is, if you go and you put in code that says only one thread is allowed to enter this area and do this work, prevent that problem I talked about before. If you have too many of those sort of things, you can end up having everybody trying to get through the same single point, and now you've basically serialized your multi-threaded code. Zombie threads we're going to ignore. Thread starvation is basically just if too many threads are doing too many things, nobody gets anything done. I know I'm trying to go through this quickly, but if people have questions, they don't understand something, let me know. If done really poorly, you can actually make things worse. Because if you serialize basically with bottlenecks, or if you deadlock, then nothing's happening. If you have your synchronization problem, you've serialized it, but you've still got all the other overhead that you've incurred from doing multi-threading. Hidden multi-threading. So basically, web applications, application services, they all, to some extent, are providing some multi-threading for you, right? You've got a server, web server, or an application server, and you can have thousands of requests coming in at the same time. They're all asking for the same page, except you're customizing the page slightly, maybe it isn't a static page. So that's a way that you're doing it. Now you're not,
I would say you're doing it inefficiently in that it isn't going to serve up as fast as if you wrote it yourself, but sometimes it isn't worth writing it yourself, right? Logging subsystems, I believe nlog and jlog both allow you to, flip a proverbial switch to tell it to write the log asynchronously. And in that case, when you do your logging, you've got a separate thread that's actually waiting for the disk to finish writing before it writes the next log line down. GUIs sometimes provide some stuff. I/O, if you go and you make a call and you say, call me back when you get the data or you finish writing it, to some extent, you're doing multi-threading because you're basically having the operating system do it. There are programming languages like P. There are different, I just went to a talk on Lambda functions. All of that is multi-threading. They're generalizing things. Access to data may not be as efficient, but it may solve your problem and give you enough of an advantage that you don't need to get into the weeds. So, quickly, what is a thread? A thread is a flow of control through the programs. It's basically a stack, a register set, code pointer, thread ID. I'm not entirely sure that they still teach this kind of stuff in colleges. I don't know if it's gotten so abstracted. You have some thread specific data. All of this together is a thread context. The way to look at it is like this. In a single threaded application, you have code, you have data, it says file, but that's really just any kind of handle. So file handles, socket handles, database handles, all of that kind of stuff. You have the register in the stack, and then you have your flow of control for your thread, for your single thread. When you go multi-threaded, what ends up happening is now you have multiple sets of registers, multiple sets of stack, and multiple threads of control. So you can be here on one, here on one, here on the other one, all executing at the same time. Or actually, in a lot of cases, they're doing different things. They can be doing different things. But the main point is, all of these threads have access to all the code, all the data, and all the handles. And in particular, the data and the handles can be problematic. If I mark something in red, it means I'm really going to this too. So basically, thread state is doing something. You're either doing something, you're sleeping, which I wouldn't recommend. Holding is bad. You're waiting for something to happen. Basically, you're waiting for an event, or you're dead. Those are your states. The main libraries are POSIX, Win32, Java's got whatever they've got. There's other things that you can do, Boost, Ace, Qtype, to try to give you a little more multi-platform, if that's what you need. But typically, this stuff is specific for them. Task-based threads. You can break up your threads based on the task. You can say, I've got a logging thread. I've got a thread that processes my main work. I've got a janitorial thread that goes through and does some sort of maintenance work. I've got another thread that, provides the logs, things like that. So you can break things up that way. One of the advantages of unrelated task-based threads is that they're unrelated, and so there's less possible conflict over resources. Typically, and this is in general, the interfaces between other threads tend to be things like toss and forget. So if you have a logging thread, typically what happens is you package up your log, what you want to log, you throw it over the wall to your coworker, the logging thread, and you forget that you ever handed it to them. You don't know about it anymore. Janitorial, not going to really go into it. Informational, the thread, is collecting performance statistics from all the other threads and then logging it somewhere. Worker pools is probably the most common example that you see when you start talking about threads. So, and the way most of the sort of higher level programs work, all the threads are doing the same task, but with different inputs. So basically, that's your back to your framing crew. You may have, 4 people, and they're all doing framing work. They're all working maybe on different parts of the house, but they're all doing the same task. You've got multiple people to try to get things done faster. Typically, you use some sort of a queue or messaging system to assign work. Basically, the work comes in, it gets put on a queue. The worker, when he's done, looks to see if there's new work. If there's new work, they grab it off the queue and they go off and do it. And if there isn't work, then it waits until work becomes available. That's typically how it's done. There's more likelihood of resource contention with worker pool threads because they're all doing the same thing. We're not going to really talk about stage threads. Basically, it's just another way of doing that. Temporary threads, don't do them. Basically, don't spin up a thread to do something and then have it go away. I mean, sometimes it's useful if you've got want to have a thread sitting around doing nothing. But the better solution is to do a command thread, which is really where I think the higher levels work. It's like a worker pool, except you've abstracted out what the work is. So you're using the command pattern. People familiar with the command pattern at all? No. Well, command pattern basically says you've got an interface. The interface for your object is very simple. It's just do. And then you implement an object, and the object has all of the data, and it knows how to implement do, whatever do is. And so you put that onto the queue, and the worker thread just picks up the thing, executes do, and then when it's done, it picks up another object and has it implement do. We're not going to really talk about this. Once again, I'm talking at a lower level. So, you've got events, which is really where you try to, it's how you notify a thread that something is happening. So you have an event that says more work is available, so that it wakes up, it signals a thread to say, go and look at the queue, see, pull some more work because more work's showing up. It's either auto reset, which means that if there's 5 people or 5 threads waiting on the event, only one will be woken up. If it's a manual reset, they're all woken up. I don't know if you really care about that difference. One of the things that is good is that wait allows you to wait on either a single event, any event out of a pool of events, or all the events. So basically, single is single. You say, tell me when, event X is single. Any is, here are 3 possible things. Let me know if any one of them. And all is when, maybe you sent out information to be processed by 5 threads. And then you say, let me know when all 5 of them have finished doing it. And then I will continue with whatever the processing is. Sleep, once again, you can use it, but I don't recommend it because polling is bad. Basically, it's done. Sleep, you're saying, sleep for 50 milliseconds, check something. Sleep for 50 milliseconds, do something. You'd rather just use the event. Join what I'm going to talk about. So, protection mechanisms. So we talked about before where, you don't want 2 threads accessing common data that is writable at the same time. So what you do is you have what they call is a mutual exclusion or mutex object specific to whatever it is you want to protect, and you create a lock. And when the lock's created, nobody else can gain the lock until the lock is released. Now, different programming language, well, at a low level, you do this manually, and you use, in C++, a constructor and destructor to make sure it always gets released. In languages like Java and C# and pretty much anything else that's more modern, they've got a syntax where it's, some sort of command word, the item you want to lock on, and then you've got your braces, and the code in between the braces won't be executed by more than one thread at a time. But they'll all be hanging out waiting. You can also have a read-write block, which works like a database read-write block. Multiple people can read at the same time, or one person can write at the same time. You have semaphores, which is basically you're in a museum. There's a fire code. You're only allowed 50 people in. The semaphore counts down, and when it gets to 50, then it won't let anybody else in. But somebody can then release a semaphore, and the next person can come in. Because incrementing, decrementing, adding, subtracting from integers is such a common thing, some libraries like Microsoft have specialized counters which are designed for that task specifically that are optimized, so they're faster than the more general things. You can set the thread priority, which I said before. We're not going to really do that. Very briefly, Windows provides a lightweight version of all of those multi-threading structures for use within a process, but they also provide a heavier version that'll work across processes and even across machines. So you pay more in terms of performance, but you can conceivably have an event fired from one machine that is signaled and accepted by a thread in another machine, which is nice if you eventually get to the point where you have to spread across machines to get work done. So basically all of these things, they've got heavier and lighter versions. A little breath. All of that very, very quick so I could get to here, but first, any questions about any of that other sort of stuff? Why we want to do it versus some other method?
Something like, so you can split things up in more things at the same time. Yep. And also, it seems like there's a lot of concern over how those separate threads are accessing the same data.
Yes.
And so where is it that you would implement some of those protections? Is that in what the code you're writing, or is that in the operating system?
It's in the code.
Okay, so you put in some of these protections in the code you're writing. Yeah. But then there's code that other people have written.
I am just talking about all code that, I shouldn't say that you've written, but your company has written. Right? Access to the actual code. All of this gets compiled into, either the Java interpreted language, the Microsoft interpreted language, or machine code as a single executable. But yes, if you've got multiple people working on the project, they all have to be aware of all of this. Any other questions?
Just real quick, does async imply multi-threading?
Yes. Async and multi-threading are basically the same thing. Because or I guess what you're saying is asynchronous threading is a way of implementing asynchronous. You could implement asynchronous by having two different processes that communicate with each other to accomplish some task. Any other questions? All right. Typically the way you enter into, when you spin up a new thread, you're calling a function or a method, you're handing it another function or method, and the operating system will spin up a thread, and then once it's all got all that together, it'll call your function. So one of the things you want to do is you want to catch all exceptions in the entry point because you don't want them to escape. I always like having a shutdown event in flag so that you can shut down, so that your system can be shut down quickly, because now you've got multiple threads. Any one of them can stop your application from closing when the user wants to. So, we can get back to that later. Another sort of rule of thumb, you want 1 to 8 times the number of worker threads as you have CPUs in your system. It depends in large part on whether or not, or what those threads are doing. If they're doing a lot of computational work, then you're going to want a lower number. If they're, accessing the disk, if they're going to a socket somewhere, going and getting making a web-based call, so they're spending a lot of time waiting, then you can have more of them. Don't create and destroy threads, reuse them, use that command pattern. Don't create threads that are rarely used on the end, the command pattern. Check that any API calls you make are thread safe. This is important. It's not as important now. I think mostly they've gotten better. But the idea is you've gone and spent all of this time. You've made sure that you're not accessing the same data at the same time. You're making sure you're not stomping on things. You've been really good. And then you call the random generator function. And it turns out the random generator function isn't thread safe. And 2 threads call it at the same time, and bad things happen. So you need to be cognizant of what you call. It could be a third-party locker. Actually, these days, that's probably a bigger problem. And it may not be thread safe. We're going to get into this a little more, but avoid locks if you can, and do that by structuring your data, and we're going to talk about that in just a bit. Use lower priority threads. Always log on a low priority thread, unless for some reason logging is really critical to your system. So before I was saying avoid locks. So one of the things that you need to do is, this comes from the fact that I like to have fewer things that are lockable, because I think it makes it easier to avoid deadlocks. Because if you just go through your code and just say, okay, I'm just going to make it so that everything is locked, and you can only, access it one at a time, then it's easier to get into deadlock. So I tend to like to group data by what it's used for. And if you separate out the read data from the write data, then the read data, you don't have to lock, and you only have to lock the write data. Organize the data for maximum separation. You want to, if there's an operation that uses 3 pieces of data all the time, then I would sort of group them together within a lock so that you get them all at once, rather than going and getting one piece. But organize it. You don't want to overly lock things, because then you're locking something that could be used for 3 different processes, 3 different tasks, I should say. And you don't want the threads all trying to get it at the same time when you can separate them out. Always have a force release of the lock. This really only applies if you're doing things in, say, C++. Like I said, Java and C# and other modern languages tend to have this as syntactic sugar. This is important. If you have to lock more than one thing, always lock in the same order, always unlock in the opposite order. This is to prevent, if you do this, you can prevent deadlock. So back to the framing example, if you have a rule that says you always grab the compressor first, then you won't have one guy grabbing the compressor and then one person grabbing the nail gun. You'll always have the first person grabs the compressor. When the second thread goes to grab the compressor, they'll be prevented. because it's already been locked down by the first person. And then you want to release it in the opposite order so that you don't screw things up in reverse.
When you separate out the read data and the write data, does that mean with the thread, what's happening in the thread?
Well, I'm saying you organize data by class, right? You say, I have a class, and the class has, the following 5 data types along with the following 10 methods. What I'm saying is you want to group your data in such a way that all your basically static or read-only objects, well, actually, you don't have to do anything with read-only objects because you don't have to lock them. But that's what I'm saying is you want to try to separate as much as possible the read-only data from the read-write data because you don't want to have more locks than you have to. And you want to try to group them in such a way that you're not, as I said, over or under not scoping, but you're not protecting things when you don't need to protect them, and you're not protecting things when you're not. A little, I don't know. A lot of this is sort of art.
Yeah.
As opposed to engineering, but a lot of what we do is like that. I like to tend to organize the data into things that are thread specific. So if I tend to think of this as almost like a workman's tool chest. So if a plumber comes to a site, he comes with his tools. If there's more than one plumber working, because it's a commercial property, each one has their own set of tools. And if they have all their own set of tools, then you don't have to protect against it because, they have their own set. There's no conflict. So I like to tend to organize things like that. Task-specific, unique. Once again, if it's unique to a task and you only have one thing doing that task, then you don't have to block it. Or think of it this way: you could have a bunch of people at H&R Block. They're all doing taxes, right? The task-specific data in this case would be an individual person's receipts, their W-2s, their 1099s, their, all the information necessary to do the taxes. One H&R Block person is going through that shoebox of receipts. They don't have to worry about the guy next to them needing any of that information. So once again, it's not shared, so you don't have to protect it. Then you have task-specific shared. That has to be locked. That's the copy machine at the H&R Block office, where you don't want one guy coming up, starting to copy a bunch of things, and then somebody else pulling their stuff out, putting in their stuff, starting the copy, grabbing stuff that contains, some of the first person's stuff plus their stuff, and then the other one's missing stuff. So that's what you need to protect. One trick that I like to use, or actually, I had a boss once who told me a smart person knows how to handle a difficult problem. A wise person knows how to avoid that problem in the first place. So I had another boss, which I should have written this down. When I first started working for a telecom company, he told me there's a difference between banking applications and telecom applications. In banking applications, it must be right. It must be perfect, down to the penny, every single time, no exceptions. Performance, while important, is secondary to accuracy. He said in telecom, things are a little different. If once every 1,000 times a person dials, the call doesn't go through, they'll dial again. It can't be too often or they'll get frustrated and you'll get complaints. But being perfectly accurate is less important than quickly making the call or quickly, hearing the dial tone when they pick up the phone. So a different set of priorities. So this example works in telecom, but not in banking. But we'll talk how we can change it a little bit to have it work in banking as well. So when data changes infrequently, and speed is more important than accuracy, so basically the telecom application, what you can do is you can take data that changes, like I said, infrequently, and you can say, I'm going to assume it never changes from the extent of that thing, right? So what you do is at the start of, well, you're doing this to avoid a synchronization bottleneck. You don't want to have everybody fighting over getting control of this information they need to read. You don't want to copy it because there's a fair amount of it. You don't want to have locks because that causes problems. But basically what you do is you have a factory object, and at the beginning of the processing, you ask the factory object, give me the current state, give me this information, and it'll give you that information. And it's just giving you a copy. It's giving you the same copy it gave the last person. It's giving the same copy it's going to give the next person. It's going to give it hundreds of thousands of times to different threads. And you use that. Now, as an example, I did this, Kroger's, they're now the third largest retailer in America. It's a supermarket chain that exists everywhere but the Northeast. Pretty much. Yeah. Excellent. So I wrote software that's used every time you swipe a card, the loyalty card. A message gets sent up to my software. My software says, this is Joe. Joe's been targeted by the marketing department for, these offers. He's also getting these other offers that everybody else gets. The particular store that he's in is, has this other offer. He's 6 cups of coffee into getting his free cup of coffee at 10 cups, all that information. And it sends it back down, and at the end of the transaction, another message gets sent up that says, they used these offers and bought more cups of coffee. So at the beginning, I have this large hunk of data which describes all of the offers, at what stores they're available, all of this sort of static information that's not quite static. It gets updated once a day, generally speaking. It can be updated in the middle of the day if somebody discovers that, they screwed up and instead of 50 cents off, they put in $5 off. So it can be updated, but it's what I call, mostly static data. Plus, nobody's going to care if at 12:01 you got the same offer, at midnight, you got the same offers as somebody in line ahead of you got. As long as, it's like 12:02 it's changed. Right? So that's where I do something like this. I say, give me all that information, because I don't want to lock it down, but it could change. In a banking application, this wouldn't work. But here, I say, give me all the information, and it saves me a lot of time, mostly because this data is a summation view of data stored in the database. So I don't want to go to the database. This is all sort of basically caching for performance. So, but it could be wrong. So you can use it in telecom. You can use it somewhere like the supermarket where they don't care if, you're getting something a little later in the day than you should have. Now, you can also do this, what I call the whoopsie pattern. You can convert this for banking applications. I'm sure somewhere there's a better name for this and somebody else has written up this pattern. But basically what that is, you get the information, you process it, and then just before you're ready to hand off the results, you actually do a lockdown of the data. You compare some sort of identity number. And if it's the same, you're like, great, I'm done, ship it off, unlock it. And if it isn't, if it changed, if midnight came, if they discovered there was a $5 instead of 50-cent coupon, then you basically throw away all the work you did, roll it back if you have to roll back something, get a new version, and then move forward. So obviously this only works if, like I said, this is semi-static data. It doesn't change all the time. It's changed every minute.
Anything like opening a cache clear in the cache?
Well, in that particular code, there's a thread that goes and monitors the database and basically tells the factory object, or actually it will update the factory object to generate a new version of this object and to start passing out the new version of the object the next time somebody asks for it. So in this particular case, I think within less than a minute, maybe even 10 seconds, you should get a new version. But basically what happens is, worker thread comes in, they get a version. Worker thread comes in, they get a version. And then at some point in time, hopefully, like I said, less than a minute, maybe even 10 seconds, they'll start getting the new version, the new one. Actually, managed to get it in 45 minutes.
Yeah.
So,
through multi-threading, are you capable of setting tasks where you can create like a Docker container depending on a triggered event? And since containers can be disassociated from each other, could that potentially prevent deadlocking?
well, okay. So, I'm not that familiar with Docker, so I can't get into specifics. However, from what I can tell, all of these sort of higher level things, because if you see, they've gone through, I guess, containers, and now we're on to, I just went to a talk on these things. Lambdas. All of these are trying to abstract out things. And that works great if things are actually independent of each other. So if you've got an application that, say, it takes a picture and removes red eye, right? So you can have, each picture getting processed for the red eye has absolutely no interaction with any other process doing red eye. And that's where things like the Docker works, or containers or lambdas or whatever, works really well. The question is when one entity, one thread might affect the behavior of another thread, and you have that resource component. So for example, in the supermarket thing, one of the things we have to be concerned about is some offers are available at the family, what we call the family level, right? And so we wanted to make sure that if, the husband went and got a free cup of coffee from the, because they bought 10 cups of coffee, that the wife doesn't also get a free cup of coffee because the two of them came in at the same time and they both bought their cup of coffee. So in that case, they're not independent actions. So typically the way things like Docker and Lambda avoid this is they just basically pretend that, that there's no conflicts. And if there is, they push it off to some other service or the database. That's another thing, is the database will enforce things for you, assuming that you have a transaction, right? So if you go, even if you're in So if you're in Docker or Lambda or whatever, and you have a transaction, and that transaction says, I'm going to add $10 to this person's bank account. If two Lambda functions or Docker things go to the database at the exact same millisecond, the database is performing that locking of the thing, so that you get so that at the end of the thing, the account's been incremented to $20 more instead of just 10 because of the conflict. And basically, the database worries about the deadline. Presumably, they get that right.
So if you're implementing the locking yourself in your application, whether it's specifically with a multi-threaded process or Docker containers or Lambda, if you're doing the locking, you can still get in problems with that locking.
Yeah.
Great, because no matter how far you spin it out, whether you're spinning it out Docker, you're still, what you're concerned with is the data that's being shared across the threads or across whatever else you're trying to do.
Yeah.
Yeah, and like you said, in transactional database, that's something that you're offloading to the database by using transactions. And doing the locking like that. Then you'll know what that is.
Yeah.
What's Kroger using for docking grocery store software? Is it like something that, were you part of the working with the company that they bought the software from, or?
Well, I mean, first of all, they're really attentive. Yeah. They're not using, Amazon or Google or Microsoft to host their stuff. They host it themselves. Yeah. Because they're control freaks. But yes, I work, actually they still pay me a retainer in case something blows up, but, I worked for a company that wrote the software that they use for that particular piece. So that particular company, I did the real-time software, and there was a group of other people who would get basically a list of everything you bought there.
Yeah.
And then they provided analytical tools to help them do their marketing. And their marketing was typically, how can we get somebody who's a tier 3 shopper and make them a tier 2 shopper, so that we can, improve our business. The scariest part about that, and that wasn't our company, but some other company, was when Target sent an ad for baby stuff to some 17-year-old girl, and the father flipped out. But it turned out Target was right. And she didn't buy a pregnancy test. She wasn't buying baby clothes. They had just discovered that when women got pregnant, they would switch from, I think it was scented to unscented products. And based on that, and I guess a few other things, they were able to figure out. And from Target's point of view, this is very important, because if you get somebody to start buying their baby stuff from Target, they have a tendency to keep buying their baby stuff from Target. They want to lock you in as a customer for that stuff as early as possible. Any other questions? So just because I've seen all these other ways that you can do multi-threading. Like I said, sort of an existential crisis in that you can do things with Lambda, you can do things with Docker, all that's multi-threading. Depending on your application, it could be as fast or almost as fast as doing it this way, which is more, custom software. If there's more interaction between things, then I think you're starting to pay a larger price. Maybe it's 10% slower, maybe it's 20% slower. Maybe there's an issue that the software I wrote for Kroger has an average response time of 40 milliseconds. They want it that fast. Not that I know that it's particularly necessary, but that's what they want. And I think you probably have issues with, using a system, like Lambda and Docker, but I'm not positive that there's no such thing as free lunch, so to speak. But it may be that using Lambdas is better for you because you don't have to worry about any of this stuff if you can avoid it. And you don't care if you're spending 10% more because the engineering cost is high.
What's your favorite way to explain to a non-technical person the difference between synchronous and asynchronous?
Well, a non-technical person.
The shopping, the checkout line was really good.
Yeah.
Like an analogy.
Yeah, well, no, I think the checkout line works well in that, you're trying to handle so many people trying to get through the system. And,
So it'd be like a single checkout line versus 6.
exactly.
Okay.
Exactly. And like I said, and I've actually gotten a job describing it this way, where I said that first slide, or not first, but one of the early slides, where I said basically, on an 8 CPU computer, you're not using 7 of the CPUs. Moore's law stopped working for you. I've used that before. But you've got to have that performance need before you get to that point where you need to look at it. So if you've got an application at work, well, I mean, I did a project for a financial company down in Wall Street, and, there was something that was taking, a minute. And it's like, well, we've got this 8 CPU machine, and you're only using 1 CPU, maybe we can get this down to 10 seconds. And, doing some other optimizations as well. But, that's where you start saying it. Cell phones, the same thing, now, they also, like I said, my Samsung is a quad-core device. So if you write a single-threaded mobile app, you're leaving 3 CPUs on the table. Though you also have to be careful, especially when it's a consumer product like a cell phone. You don't want to suck all the power out of it, or else they'll take that.
What was that ratio again that you said for how many threads you should have running?
I tend to go somewhere between 1 and 8, but it really depends on what the thread is doing. If the thread is accessing the disk, well, disks are slow. If it's accessing a database, which is accessing a disk, that can be slow. If you're accessing a microservice available God knows where in the world, because you're just sending it up there, that can be slow. And so you can have more. On the other hand, if you're doing color correction of visual, of images, that's almost all crunching of numbers, and so you're going to want to be much closer to 1, maybe even less than 1. But you're going to want to be closer to 1 because it's spending all of its time actually doing CPU work.
So there's been a couple of questions about synchronous versus asynchronous, and there's a distinction I think to be made between that and multi-threading. I'm not completely 100% on this, but I'm working on a lot with Node nowadays, and in Node you can do asynchronous or synchronous JavaScript, but that can be run in a single thread or process because it's event-driven. And so that's like, if you want to do that reading, actually find out the distinctions, you can dive in and figure out the stuff underneath. But you can also, I'm pretty sure, run Node with multiple threads or processes, and it's actually a little bit faster when you're doing these things stuff because it's able to actually, hit all these things. Otherwise, it has to actually stop the real work and do some garbage collection every once in a while. and then go pick it up and do normal stuff. Whereas otherwise, if it actually has multiple threads, it has a dedicated garbage collection thread. It's picking that stuff up for you, so the whole area is, stuff.
Pet peeve of mine is garbage collection. I tend to think of garbage collection as a technical solution to a educational problem. But that's just. Anything else, or?
Thank you.
All right, well, thank you for hanging out with us.
Do you have any that you recommend for getting a more like, I guess, high level overview of multi-threading? Yeah.
You know, honestly, I wish I did. I mean, the book I learned a lot of stuff from was, thank you. The thing I learned most of my stuff from was like back in 1997.
Oh, okay.
It's not exactly up to date.
Yeah.
So, yeah, I wish I did.
That's
sorry.
definitely something I do want to get a better understanding of,
Yeah.
because like you said, there's a lot of technologies that are integrating multi-threading, but it's kind of done for you. So
Yeah.
obviously, if you have a better comprehension of why it's doing that, it could end up being much more useful down the line.
I think so. And also to, somebody's point, my guess is that you can, if you're aware of the details, you might approach things slightly differently, even in the environments in which they're managing a lot of it for you.
Yeah.
And you can do a better job, and maybe, maybe you start having some microservices, like for example, the thing I was doing with the caching of information for performance reasons. In an environment like Lambda or Docker, maybe that factory object gets replaced by a microservice that provides that information for you across all of the things. Or you have some other microservice which is where you send things that, there's some sort of conflict, and you're not using a database, or for whatever reason you're not, doing it inside of a database, but you can provide that locking and transactional stuff. So yeah, I should write down to look for a more recent book, because like I said, I don't even think the book that I learned from is in print.
Oh, man.
There's some good resources depending on the environment. What are you working in now?
Well, I'm mostly doing DevOps related content, but I do some front end stuff as well, mainly through AWS.
Okay.
But
what's your language, what's your framework, what do you use?
right now I'm using Drupal.
Okay.
So I know that there's a couple pretty well with like Docker for HP, as well as some custom ones like Lambda.
Yeah, I'm trying to think of any good resources for that.